So, recording now. This is going to be the written homework problems for week 3. Just to preface this, problem 2 is actually different from the problem 2 that I had for Physics 131. So I'll be uploading this document to the Google Drive link in order for you guys to have the other problem that we had, because it's totally different. And so that'll offer you guys some extra practice, and then I'll have my solutions to that extra problem as well. And I believe there's part C to this problem that we had as well in my year. And so, like I said, I'll just upload that document that I had for you guys to have extra practice, so you can see different types of problems. So hopefully that helps as well. Like I said, everything's going to be in the Google Drive and the YouTube. So hopefully everything goes well and you guys are able to access that. It's a little blurry. Okay. I zoomed in a little bit. Is that better now? Or should I refresh? Maybe refresh. Okay, 1 second here. Stop share. Share screen again. What time? Okay, there we go. Is that better? Hopefully it is. Past couple of meetings, Zoom has been okay with the refresh stuff, so just let me know in the chat if it's still blurry or whatever. But are we good to go? Yeah, okay, cool. So, first problem, using free body diagrams. So, part A, says the free body diagram at the right shows the forces acting on a 2 kilogram object. It says to use Newton's second law to find AX and AY, right? So, first of all, Newton's second law is F equals ma, right? Force is equal to mass times acceleration, right? So that is Newton's second law. We need to find out both the acceleration in the x direction and the acceleration in the y direction, right? Those are our two unknowns that we need to figure out. Now, with regards to forces in general, forces are either a push or a pull or some kind of, effect that you can cause on an object. And the person or the entity that is going to be causing that force, that push or a pull, is going to be the agent of that force, right? So if I'm throwing a baseball, I'm the agent, and then the force that I'm exerting on that baseball is some kind of, let's say, like throwing force or a push force, technically, right? Throwing that ball in the air, for example. So a force is kind of like a push or a pull, right? And then force is equal to mass times acceleration, and then you have an agent or some kind of entity acting to exert that force on a specific object. Now, we have here 1, 2, 3, 4, 5 forces, right, acting on this object that is 2 kilograms. And we want to find out both the acceleration in the x direction and the acceleration in the y direction. So, hopefully you guys can see this writing. I haven't written anything down yet, but let me know if the writing is blurry or if it needs to be refreshed. But basically, you have F net x and F net y, right, as the two components of the net force that you're trying to figure out. Can you guys see the F net x and F net y that I've written down? Okay, let me try and refresh and see. Hopefully you guys can see it now. This is ridiculous for Zoom. Okay, can you see the writing now? Okay, excellent. All right, this is F net x, F net y. So net force components in the x direction and the y direction. So when you're calculating some kind of acceleration in the x or acceleration in the y, we're dealing with forces, we have to separate things up into net force in the x direction and net force in the y direction, right? So according to this little equation that we have here, F equals ma, we have F net x should be equal to max, and F net y should be equal to may, right? Make sense? So in that case, it's a matter of looking at which forces are acting in the x direction, which forces are acting in the y direction, and then kind of assigning them to each little equation, right? So for F net x, we have a 2 Newton force to the left, 4 Newton force to the right, and then for F net y, we have 3 Newton force up, and then a 2 Newton and a 1 Newton force pointing downwards. So if we're just going by our normal coordinate directions that we know and we're familiar with, we know that the positive x direction, that's positive, right? And the negative x direction, this way is negative, so like east, west, north, south, if we're going by cardinal directions, right? Positive y, right? Positive y, negative x, positive x. So in that case, we can write F net x, for example, as the sum of the forces in the x direction, right? So what your professors will often do is basically set up the equation as literally the sum of the forces. Like they add up every single force without respect to the direction. That's very common, and that personally confused me. So I wrote my equations a little bit differently. I found that to be more helpful, but whatever way works for you, works for you. So what your professors are going to do, they're going to say, for example, okay, let's label this F1, this F2, this F3, F4, and F5, right? So we have F net x being equal to F1 plus F2. That's how your professors are going to write it. Now, in that case, that means that your F2 force, for example, here, we can clearly see that's in the what direction? Let me know in the chat or unmute. This 2 Newton force. Negative x direction, right? So it should be a negative force. So when I'm plugging this value here into the equation, I should say, well, F1, right, plus, and then this is negative 2 newtons. I have to write that down. I have to make sure I include the negative sign in that sense. However, the way I prefer to do it is if I just go ahead and integrate the direction of everything within the equation itself, and so I just have to put in the magnitudes. So if I say F1 minus F2, well, this little minus sign right here is indicative that that force, that F2, right, is in the negative x direction or in the negative y direction, for example, if we're talking about F net y. So that negative signs in the F net equations, I would put negative signs in there to automatically indicate your directions, so you only have to worry about putting in the magnitudes of the forces into your equation, right? So, okay, let me refresh again. Someone told me that you guys can't see. This is just fantastic. It was working every single session before, and today it's not. So, to repeat that again, F2, if it's in the negative x direction, right, we can just integrate the direction into the equation itself instead of saying F1 plus F2. So if you just integrate the direction in the equation, it just makes things a lot easier. So that way we can say F net x is equal to F1 minus F2, and we can just plug in, okay, this is 4 newtons, and this is 2 newtons, right? So I can say 4 newtons minus 2 newtons, right? And that should give me a F net x of 2 newtons, right? Now, that's my F net x, right? My F net y, on the other hand, same deal, right? It's just a matter of looking at your directions here and then putting them into equations. So anyone want to give it a shot as to how they would set up their equation, like F1 minus F2 or something like that? How would you model these three forces in the y direction? How would you write an equation for that? So F3 minus F4 minus F5. Yep, excellent. Absolutely right. Because in that way you integrate the downward or the negative y directions of both F4 and F5, and you don't have to worry about plugging in, you know, the negative 2, for example, like this example here that I had earlier. So in that case, you can just say F3 minus F4 minus F5, and you don't have to worry about putting an extra negative sign or anything like that. You just literally just go ahead and put in the magnitudes of all the forces, as long as you integrate your direction within the equation itself. So for F3, right, that was 3 newtons, and we already indicated that this is positive, right, because we didn't have a negative in behind it. Okay, someone told me that the writing is not showing up again. This is phenomenal. Okay, can you guys see the F3 minus F4 minus F5 here? Okay, great. F3 is positive, right? Because we indicated that it's positive here in the equation already, so we just plug in the 3 newtons. And then we have F4 is minus 1 newtons. F5 is minus 2 newtons, right? So in that case, we can literally just solve for it. And we can see here 3 minus 1 minus 2, that's going to give us 0 newtons for our F net Y, right? Now, we got our F net, our net force components X and Y. All we have to do now is set them equal to MAX and MAY to figure out AX and AY. So those are the two variables we're trying to solve for. So if we know that F net X is equal to 2 newtons, right? So if I can just go ahead and erase this and say that F net X is equal to 2 newtons, and that's equal to MAX, right? And this is equal to 0 newtons, and this is MAY. Frozen again. All right, I'm just going to have to stop using Zoom for the next session. I'll update my links and all that, because it just looks like if there's more participants, then it just gets a little hectic. So thank you to those who are notifying me about the frozen screen, but it's not frozen on my end in terms of the screen recording. So if you guys miss anything or if anything's confusing, just let me know right now. Or obviously I have the recordings uploaded within like 10 minutes after the session, so you can refer to that as well if you're missing something, but hopefully we can get everything taken care of now. So we have 0 newtons equals MAY, 2 newtons equals MAX, right? And we know the mass to be 2 kilograms. So if we adjust this to be 2 kilograms times AX, and then if you are pretty observant, you realize that it doesn't matter if we put 2 kilograms here or 3 or whatever, right? Because the F net Y is 0 newtons. So this whole thing, obviously, 2 times what is equal to 0. So this is AX. I should write AY. AY is equal to 0 in that case, right? I see some questions here. Can you repeat why we don't include the negative sign? So if you go ahead and write your equation like this, where you're integrating negative signs automatically, you can just go ahead and put in the magnitudes, right? Because you've already included that negative sign. However, if you want to do it the way the professors do it, which is, okay, if we do that same example here, F3 plus F4 plus F5, in that case, you would have to put the negative sign. So you'd have to say, okay, well, F3 is a positive 3 newtons, and F4 is a negative 1 newton, and F5 is negative 2 newtons. So if you just add everything up, right, F3 plus F4 plus F5, or F1 plus F2, then that's when you would have to include and make sure that you're cognizant of the directions, because otherwise, this is the method I prefer, which if I just integrate the directions automatically, I can just plug in the magnitudes. So if I know F4 is in the negative Y direction, I'm going to put a negative in front of it. If I know that F2 is in the negative X direction, I put a negative in front of it. And so I just get done with the whole direction thing from the begin with and not have to worry about plugging negatives and messing things up later on. Now, does it matter how you label the forces? F1, F2? No, not at all. You can label them whatever you want. You can say that this is, you can do variables. You can say Fx, Fy, Fg, Fm, whatever. So it doesn't matter how you label them, as long as you're putting them in the right F net equations, basically. So if these two forces are in the X direction, we better see them in the F net X equation. If these are in the Y direction, we better see them in the F net Y equation, or right here, F net Y equations. So it doesn't matter what you number them or label them. It's just, you just have to be wary that you put them in the right net force equations. Does that make sense? Cool. Alrighty. So going back to the problem here, we have F net Y is equal to 0 newtons. And I'm writing things down, so please let me know if you guys can't see it or if I need to refresh. But we have F net Y, that was 0, and that was set equal to MAY, right? If this is equal to 0, then regardless of what you have for the mass here, this has to be 0, right? So AY is equal to 0 here, and then we can solve for the AX here, and that's just going to be AX is equal to 1 meters per second squared, and this is meters per second squared as well. So that's your AX and your AY, right, for part A. Any questions at all about part A in terms of setting up your net force equations, the components especially F net x and F net y, determining which, forces to put where, and then how you integrate directions and stuff. Yes, the recordings are all recorded. I have a Google Drive link, and I can post that. Actually, I'll just go ahead and post it now into the chat so you guys have access to that. Because like I said, this whole freezing thing, if it just keeps up, then we can either take care of it as best as we can now, or we can, you guys can, I guess, refer back to the recording. So there's the YouTube channel where it's going to be found. And then, one second here, let me get the Google Drive link out as well. Okay, get link, copy link, and there. So there is the Google Drive link and the YouTube channel. All right, so if everyone is okay, we can go ahead and move on to part B here. Sound good? Everyone ready? Yes? Okay. Awesome. Alrighty. So we have part B here. It says you have a 50 kilogram box and it's pushed to the right along a horizontal rough surface with a force of 300 newtons, right? It accelerates at 4 meters per second squared, and you can assume the drag force is small enough to be neglected. All right. So, the problem with problems like these, right, is that there's a lot of implicit work that needs to be done. So, what does that mean? Well, we have the mass, right? We know that the mass is 50 kilograms, right? We know the force, F push, for example, since we're pushing a box, is 300 newtons, right? And we know the acceleration is equal to 4 meters per second squared. They just say acceleration. That's it, right? So there's a couple things that are not quite clear yet. So we know that the force push is along the horizontal axis, right? And it's, what, 300 newtons, right? That's F push. And we have the acceleration 4 meters per second squared, and the mass is 50 kilograms. Now, the issue here is that they don't really say what other forces are acting. Not necessarily, right? So, anyone have any ideas what other forces might be acting on the box? Because the issues with these problems is that they'll give you a force that is going to be acting, but there are a lot of other forces that you might or might not need to include, right? For example, they said here that you can neglect the drag force. So, other than the drag force, do we have any other forces acting on the object? Awesome, we got two. So, we have normal force, right? And we have gravity. So, naturally, gravity is pointing always downwards, right? We know that force of gravity is pointing downwards. Now, normal force, the way to define normal force is it's the force that is perpendicular to the contact surface. So if my contact surface is horizontal here, perpendicular means forming a right angle with. So it could be this force up here or down here, right? Like that, because they're both forming a right angle. Now, how do you figure out which one is the normal force? The way I usually think about it is the normal force is basically the force that is going to prevent you from sinking through a floor or falling like through a wall, right? Or I guess going through a wall, basically. So for example, if I'm on a floor here, right, and I have this box, or if even I'm standing over here, right, then there is a force that that floor is going to exert back on me to keep me from sinking through the floor. At the same time, if I have a wall, right, and let's say I'm leaning against the wall here, like I have my hand, let's say I have my hand against, that's a ridiculous drawing, but let me draw that again. So if I have my hand here, right, against the wall, once again, horrible drawing, but you get it. The force that's going to be acting to prevent my hand going through the wall is that normal force. And you can see here that it's, someone told me that something, or the screen needs to be refreshed. Okay, awesome. Let me refresh it again. Alrighty. Hopefully you guys can see that again now. So, yeah. Alright. If you have a wall here, you have my hand, for example, pushing against that wall, then the normal force is the force that's going to be acting against my hand to prevent it from moving through the wall. So if I'm pushing this way, right, then the normal force has to push the other way, perpendicular to the contact surface. So the contact surface is this wall, it's vertical, then my normal force is going to be pointing in whatever direction that's going to be opposing the object, right? So if, like I said, if my hand is there pushing this way, the normal force is going to be pushing in the opposite direction to prevent my hand from going through the wall at a perpendicular angle, right? At a right angle there. So if, for example, if I have my hand on the other end of the wall pushing this way, the normal force is going to push to the right instead of the left. Still at a right angle there, because like I said, the normal force is the force that is perpendicular to the contact surface. So normal force, two ways to figure it out is it's perpendicular, right? Forming right angle with contact surface, right? And two is that you got to think of it as the force that is preventing an object from sinking through a floor or going through a wall or something, right? So there's the force that's going to be giving solidity, I guess, to that surface. So think of it as the force preventing objects from sinking to the floor or going through a wall. That's how I usually kind of think about that as in an informal manner. But yeah, that's kind of what the normal force is. That's how to think about it. You have to look at the force that's perpendicular to the right, or perpendicular to the contact surface, and then think about it as the force holding an object up, preventing it from sinking to the floor. In that case, that would be in the y direction. And then if you have like your hand on the wall, right, that would be the force that's preventing you from going through the wall. So that's going to be in either in the positive x or negative x direction, depending on, I guess the directions that you've kind of defined, and then what direction you have your hand pointing in and stuff like that. But in this case, since the contact surface is horizontal, the normal force is going to be in the y direction. And since we have this object here, right, to prevent it from falling through or sinking through the floor, it's going to be pushing up. So the floor is going to be pushing up against the box to prevent it from sinking through. So this is our normal force here, right? Now, there's one more force actually that no one has mentioned yet, but it's very, very implicit. And you have to be really careful when you're looking at excellent friction, right? So rough surface is the key here. They say box pushed to the right along a horizontal rough surface, right? They don't really say friction anywhere here. They just say rough surface. If there's a rough surface, more likely than not, there's going to be friction, right? So what type of friction do we have here? Is it kinetic? Is it rolling? What do we got? Because we have a box that's being pushed along that rough surface. So it should be what type of friction? Or is it static, for example? Kinetic, right? F-K prime. Kinetic friction, because kinetic friction is the friction force that's going to be acting when you have an object sliding on a surface. You have your static friction. That's going to be friction force kind of acting to sort of, I guess, kind of prevent an object from moving, basically. And in terms of like, I guess that's a little weird because friction will prevent you from or move against your intended motion. But for static friction, we're going to get into that in the next couple of weeks a lot more. But usually the go-to examples think of static friction as like if you're parked on an incline, right? You have your car. Let's say this is a car, right? And you're parked, and so you have this static friction force that's gonna basically prevent you from slipping, basically. More or less, the static friction force is the friction force preventing slipping, right? So if you think about that car, right, that car could slip down that incline, but there's a static friction force kind of between like the tires and the road that's going to prevent that car from slipping, basically. And then you have rolling friction. Rolling friction is almost never used in any of our physics problems, but rolling friction is more like if you have a wheel or something, and it's very, very trivial, and we don't usually consider it, so I wouldn't even worry about rolling friction. Anyway, those are all our forces. Let me erase this here for a sec. Those are all our forces acting on that object. Let me reshare again, I guess, because it's frozen. All right, hopefully now everything is kind of back up again. Alrighty, so part A is now asking us, on the diagram at the right, draw and label a free body diagram, or part 1, I'm sorry. So we already got that done, right? Because we have our forces here. We've labeled them Fg for gravity, Fn for normal force, 300 newtons for the F push, and we have Fk prime, or that's the kinetic friction in that case, right? Now for part 2, we need to use Newton's second law to find the magnitude of the friction force, right? So what is Fk prime? We need to figure that out, right? We know Newton's second law, once again, is F equals ma. Whenever you hear or see Newton's second law, think of, okay, I need to start writing down some kind of F net equation, right? Maybe F net x, maybe F net y, figure things out that way. That's kind of your clue or indicator there. And so if we're wanting to find the magnitude of the friction force, do you think we're going to be concerned with forces acting in the y direction? No, right? Because Fk is firmly in the x direction, specifically the negative x direction. And there's this push force, right? 300 newtons that we know that's acting in the positive x direction. Now, once again, if we kind of refer back to this problem, the reason why we can think of the y directions kind of being negligible is that the box is being pushed solely to the right. So we have no indication here that this box is moving in the y direction at all. So in that case, right, the box isn't like levitating and it's not sinking through the floor or anything like that. So if they were, for example, to ask us Fn and Fg, what are those values, right? Well, we know the box is 50 kilograms, so we can easily figure out Fg because Fg is equal to mg. So we just take 50 kilograms times 10 meters per second squared to get 500 newtons. That would be our force of gravity, right? And that would be negative 500 newtons because that's pointing downwards. And then our normal force would just be a positive 500 newtons. So they would cancel out basically because there's no indication here anywhere in the problem that there is some net force or net movement at least in the y direction, right? It's not levitating and it's not sinking through the floor. So that's why we can kind of neglect the y direction forces and focus more on the x direction. So for F net x, we have F push to the right, and then we can say minus Fk prime, and that's F kinetic friction, right? And like I said, I'll just integrate the direction right then and there with the equation. So we have F push minus Fk prime, and then that's equal to max, right? Well, once again, assuming that this box isn't levitating and it's not sinking through the floor according to the details given in the problem, well, we know the acceleration to be 4 meters per second squared, right? We already know that. And we already know the mass as well. So we have 50 kilograms times 4 meters per second squared. So we can automatically fill in those two blanks right there for those variables. Now for F push, we also know that, and that's 300 newtons. The only thing left to figure out is Fk prime, and that's exactly what we need to figure out for part 2 here. So that being said, right, we have here, this is, if we want to rearrange the equation, right, we have 50 times 4 is equal to 300 minus Fk. So we can say that, okay, 300 newtons minus 50 kilograms times 4 meters per second squared is equal to Fk prime. I think, did I mess something up here? No. I'm good. Yeah. So Fk prime is then equal to 300 newtons, and this is going to be 200 newtons. 50 times 4 is 200. How did I get 500 for the y-axis? So for the 500 newtons was just kind of like an example of how to figure out the force of gravity. Force of gravity is mass times acceleration due to gravity, and so that's 50 kilograms. That's not a good 50. One sec. 50 kilograms times 10 meters per second squared, and that would give us, and then obviously we'd have to integrate the direction there, so it's negative 500 newtons for the force of gravity, or 500 newtons pointing in the negative y direction. Does that make sense for how I got the 500? That was just more of like a theoretical example, like if they were to ask you what Fg is or what Fn is, that's how we'd figure it out. Yes, the 10 is coming like from the free fall. That's acceleration due to gravity, so that's 10 meters per second squared. Yep. And if you think about it too, like since acceleration due to gravity is always pointing downwards, I would actually like just go ahead and say 50 kilograms times negative 10 meters per second squared. And then that's a negative 500 right there. Because that way you don't have to, that's another example of integrating directions, because acceleration due to gravity is always pointing downwards. And so there's a negative sign right there within the gravity, within the acceleration due to gravity. And so that'll give you the negative 500. Otherwise, if you just put 10 meters per second squared, you're going to have to integrate the direction later on. So we have a question here about Fk prime, how I made the Fk prime distinction. Do you mean like how I know that it's kinetic friction and not like rolling friction or sliding friction? Okay, so for Fk prime, the way I figured out that it was kinetic friction and not like static friction or rolling friction is that it says the box is being pushed to the right along a horizontal surface. So I'm pushing something, this box here, along the horizontal surface, right? I'm already technically past the static friction, because static friction will just prevent an object from sliding when it's at rest. So like I said with that car example, if that car, gosh, I can't draw a car ever. If that car is on that incline, right, and it's parked there, there's a static friction force that's going to keep it from, this would be Fs prime, F static, right? That's going to keep it from slipping down the hill when it's at rest. That's the static friction force. So static friction is more like the friction force that's keeping something from slipping when it's at rest. Or, in other words, like, because that would be the example for the car problem when it's inclined or parked on a hill. But for next couple of weeks, we're going to be doing things with like centripetal motion and centripetal acceleration. And in that case, there's a static friction force that also helps you kind of turn. So in other words, if you're turning, for example, at an intersection, you're going this way, there's a static friction force that's going to keep your tires from slipping. And it's generally always being pointed radially inward or to the center. But we'll get into that next week or the week after, I think. But yeah, generally, the static friction force is the force that keeps things from slipping. And so there's no slipping anything here with a box, because it's just, we're firmly pushing it at a constant acceleration across that horizontal surface, right? We're not making any turns or anything like that, and it's not at rest. And so it's also not rolling friction, because it's not a ball or something like that, or a wheel. So think of rolling friction as like rounded things that can roll. So that box can't necessarily roll, right? So there's F rolling friction out the window and F static friction because it's not slipping out the window as well. So kinetic is always like things sliding across the surface. So if you have a sled sliding across an ice rink, right? If you're ice skating, that's going to be kinetic friction. So kinetic friction is sliding. Static friction is like slipping. if you're at rest or if there's turning, right? If you're turning your car at an intersection, for example. And then rolling friction is with like wheels and stuff, but forget rolling friction at all because like I promise you there will almost never be a problem about rolling friction ever. But does that make sense with the whole FK prime thing? Okay, cool. So with FK prime we have 300 newtons minus 200 newtons. That should be a net 100 newtons for the magnitude of the friction force. And so this is once again why it's really handy to integrate the directions already. Because if I integrate the directions into my equations, these are all magnitudes, right? This is 300 newtons, this is 100 newtons here. We figured it out. And so if you integrate those directions and they ask you for magnitude at the end, you're already set. Otherwise, if you did F push plus FK prime, right? If you did plus, then you're going to end up subtracting this 300 newtons on this side, and you get 200 minus 300 newtons. And that's going to be a negative 100 newtons. Same 100 newtons, it's just that the negative sign at the very end as your final answer is also correct, but it indicates the direction. We only want to figure out the magnitude, so we just want the absolute value of the force. So yes, this, like if we were saying, okay, this is negative 100 newtons, right? FK prime is negative 100 newtons. However, the magnitude of that kinetic friction force is 100 newtons, and that's what they want. At the same time, with this magnitude, you're left the freedom at the end to say, okay, this is 100 newtons in the left direction or in the negative x direction or whatever. So it just depends on the way you've set up your equation. So if you choose to integrate your directions, your final answers are going to be in magnitudes of the forces. If you don't integrate your directions, so if you put plus, plus, plus for everything regardless of the direction of the force, then you're going to end up with a direction, a negative sign or a positive sign depending on the direction of the force at the end. So in this case, if I put plus sign here and I solve, I should get a negative 100 at the end, and then I have to take away that negative 100 by just taking the absolute value. So if this was negative 100, if I take the absolute value of negative 100, it should give me 100 newtons because I want to find the magnitude in the end. And so yeah, the net force, or the net, not the net force, my bad. The FK prime here is 100 newtons. Now, don't confuse this with the F net x because the F net x is equal to MAX, and MAX, we already figured that out to be 50 kilograms times 4 meters per second squared. The net force would be 200 newtons, right? Which makes sense because in that case, well, if there's 100 newtons pushing to the left and 300 pushing to the right, 300 minus 100, right? 300 minus the 100 here, right? That should give us a positive net 200 Newton force. F net x is 200 newtons, which is 50 times 4 right here, which makes sense because if we're pushing this thing to right, the only way we're going to be pushing it to the right is if we have some positive net force to the right. Makes sense for part B? Any questions at all about anything for problem 1? Yes, the answer for this one here, so we're trying to figure out friction force, the magnitude of that friction force. So Fk prime, that friction force is equal to 100 newtons. That's its magnitude. Yeah, you wouldn't say F net is equal to 100 because that would indicate that the overall net force is 100 newtons, but it is actually 200 newtons because F net x is equal to MAX, right? And if you put in 50 kilograms as your mass, 4 meters per second squared as your acceleration, you should get 200 newtons for your overall net force. But if we have 300 newtons minus the 100 newtons here for the magnitude of the friction force, then we get 200. So your magnitude of friction is 100 newtons. Any other questions? You guys can see the screen too, right? I just want to make sure that I'm just not writing some random stuff and you guys can't see it. Okay, awesome. All right. If there aren't any other questions about problem 1, we can probably just move on to problem 2 then. So problem 2, very similar, basic kind of principles here for problem 2. It seems very lengthy, but it actually is probably the easiest problem on here. And so I don't have access to an answer key for this problem 2. So technically I don't know if what I'm doing is 100% correct, but let's rely on the fact that I did well in this class, and so I should know what I'm doing to a certain extent. But yeah, so please let me know if anything seems off or if you don't understand anything, and I'm happy to go over it and recheck my answers as well. But I'm fairly confident that I've done these problems correctly because I've did them before and made sure to double check and triple check that I have everything down to a T. So that being said, problem 2, pulling luggage on a rough floor. So it says, consider a woman pulling her luggage at the airport. Luggage is L with a strap S. The strap right here is S, right? And so it says, use E for earth and F for floor when labeling your forces. Include subscripts and superscripts when labeling your forces in your free body diagram. You may drop the superscripts when doing the calculations. Use the usual coordinates. X is horizontal, Y is vertical. So is everyone familiar with superscripts and subscripts? Looks like I need to refresh here as well. Okay, there, refreshed. Yeah, is everyone familiar with the whole superscript, subscript thing? Okay. In case maybe 1 or 2 people are shy and not sure exactly what the superscript, subscript deal is with forces, it's basically an indication of not only what type of force is acting on the object, but also which agents are acting on what objects, right? So your subscripts, like your FG, your FN, right? Those are gonna be at the bottom. They're sub, right? They're underneath the force F right here, right? And so those are going to indicate what types of forces you have: gravity, normal force, right? Stuff like that. Kinetic friction, K prime, for example. And then your superscripts are up here. So if we have, for example, force of gravity, that's usually going to be Earth. So Earth is the entity or the agent, and that's acting on, and we have this little arrow, and let's say Earth on luggage, right? So force of gravity, Earth on luggage would be your subscripts and superscripts when labeling your forces. So for part A, they want us to draw a free body diagram for the suitcase to determine the X and Y components of each of the following forces. So from the begin with here, we can try and go ahead and label all the different forces that we have. Anybody want to give a shot, shout out some forces or type them in the chat? Normal force, friction, gravity, awesome. So we have normal force. Start out with that first. So we have, just kind of recap, this is our contact surface. This horizontal surface here is our contact surface. So it should be perpendicular to the contact surface. So it should be this way or that way. But like I said, since the normal force, you should think about it as the force that's keeping an object, or keeping that surface solid basically, and keeping an object from sinking through the floor or moving through a wall, right? Then this normal force would logically be pointed upwards like this. And then we have force of gravity that's always directed downwards, right? And then we have, someone said tension force, so excellent, there's tension force, right? There's FT. And then there's, someone say friction, yep, friction. So we have little itty bitty friction force, and this is going to be kinetic friction again, because it's this luggage sliding across the floor. Now, you would think that, okay, well, there's some wheels, right? So why isn't rolling friction? I'm going to be honest, like, I don't have the best answer as to why it's not, Apparently, rolling friction does play some kind of like factor, I guess, but we usually just go ahead and ignore it and just say that it's kinetic friction because those wheels are technically sliding, I guess, on the surface. Like I said, the whole rolling friction thing, like it's almost a myth in physics. Like I've never seen a problem where we've had to integrate rolling friction. Like maybe once in a very, I guess, uh, what's the word? Very trivial and very stupid practice problem, extra practice problem that is. And so it's very, very rare that you're going to see rolling friction. So I wouldn't even worry about it, to be honest, unless they specifically mention something about it in the problem. But for anything sliding on the surface, it's going to be kinetic friction. So there are forces. Those are our subscripts. Now we got to include some superscripts, right? So for gravity, what's acting on what? What entity is acting on what object? Yeah, Earth on luggage. Excellent. So Earth on luggage. So the force of gravity is due to the Earth, right? And that's our agent, and that's acting on this object here, the luggage, right? Now, for normal force, what's acting on what to exert that normal force upwards? Always think about these superscripts too as like some agent acting on the object. And so if we know that the object is luggage, it's always going to be something acting on luggage, blank acting on luggage. So someone said the Earth. Well, for these forces, you're always going to, the whole Earth on the object thing, that's always going to be gravity. But yes, the second one is right, the floor. So the floor on the luggage is absolutely right because we have floor on luggage, right? And that makes sense because, like I said, it's that force that the wall or the floor or whatever, solid surface that you have, the contact surface, is going to be exerting on the object to prevent it from sinking through or falling through, right? So this floor here is pushing up against this luggage here, right, to prevent it from sinking through the floor. So it's the floor pushing up, acting against the luggage, floor on luggage, right? Now, for this kinetic friction, what do you think that's going to be as well? Excellent. Yeah, floor on luggage. Floor on luggage, right? Because that floor is rough. You said that the floor, I think, did they say it was a rough surface? I can't remember. Yeah, rough floor there. So rough floor, so you have kinetic friction. The floor is exerting some kind of friction force on the luggage itself. Now, that's going to be our superscript for kinetic friction. And then for tension force, what is that? What are our superscripts for the tension force? Let me kind of write it over here. So we have something on luggage. Strap, right? Or the rope, right? Whatever you want to call it. Strap on luggage. So those are all of our superscripts and subscripts for the part A here of the problem. Now, there's a bunch of parts here, but they're all not too bad. So we have to figure out all the X and Y components of the different forces acting on the luggage. So there's a gravitational force, right? Given that the mass of the suitcase is 12 kilograms, we need to figure out the X and Y components of gravity. In this case, do we have an X component to gravity? No. right? So this should be 0 newtons here. Gravity's pointing solely downwards, right? The force of gravity isn't the only time that you would really have an x or a y an x component actually, because you're always going to have a y component to gravity, but the only time you would have a x component to gravity is if this object were on an incline. So if this was like a box that we're sliding up this hill or this incline, right? Gravity points directly downwards, right? And so then you'll have this little FGY and FGX component. And so there's going to be an angle here. This angle theta is equal to the angle of the incline. So if the angle of the incline here is 30 degrees, this angle here is also 30 degrees, right? And you can use trigonometry to figure out the x and y components of gravity. But in general, only time you're ever going to have an x component to gravity is if that object is somehow inclined and has an angle here, right? Because then you would have to actually adjust your x and y coordinates, because normally you have them like this, but then you have to do what's called tilted coordinates. So you have to tilt your coordinates like that, where this is x and this is y, to kind of be in line with the incline or that hill. Does that make sense? For why there's only only a y component to gravity in this case. No, it doesn't. Or that actually, never mind. That's no to the FGX for having a component. But yeah, does that make sense for how you would have a x component to gravity? Okay, cool. Now for the y component of gravity, that's pretty straightforward here, since it's only in the y direction here, directly downwards like that, right? There's no angle or anything like that. We don't have to use trig to figure things out. What would Fg equal? It would just equal mg, right? We know that. And we know the mass is 12 kilograms. And then your gravity. Here, like I said, I would integrate the direction automatically. So I would say negative 10 meters per second squared, because acceleration due to gravity is always pointing downwards. So even if you have something in free fall, if you throw something in the air, for example, right, at every instant along that path, force of gravity and the acceleration due to gravity is pointing downwards. So it's always negative g, or your value for g here is negative. That's if you choose to integrate the direction, and then therefore you would get an answer at the end that's integrating the direction. So if you have here, this would equal negative 120 newtons. And so they didn't ask for magnitude, and that's key, right? Because if they didn't ask for magnitude, we have to indicate the direction here somehow. We can either say, for example, this is 120 degrees, or 120 newtons pointed directly downwards or in the negative y direction, or the easiest way is to just literally just throw in the negative sign for the acceleration due to gravity, and you'll get your negative 120 newtons. Make sense for part A there? Cool. With regards to friction, now you see they want us to indicate the actually no, my bad. So they said magnitude of the friction is 10 newtons. They want us to figure out the x and y components, right? So they already gave us the magnitude. Now we have to indicate directions when we're looking at the x and y components of the kinetic friction. So is there a y component to kinetic friction here at all? No, right? The kinetic friction is solely pointing in the x direction. So, what's that? I think put that person on mute there for a second. But okay, sorry about that. yeah, no my bad, no friction force in the y direction because it's only in the x direction. Yeah, no worries, Matthew, no worries. But yeah, Fkx is the only component that we're going to have for the kinetic friction force. So this Fky should be 0 newtons. And then we have to indicate the direction here. So this is in the negative x direction. And we know that the magnitude of the friction is 10 newtons. So we have to throw in a negative sign, negative 10 newtons, to indicate that this is a force pointing in the negative x direction. Does it make sense for B as well? 10 newtons was in the problem here. They said friction from the floor given that the magnitude of the friction force is 10 newtons. Yep. So yeah, negative 10 newtons. No worries. Gotta be careful, guys, on if you guys have your mute on or not. So yeah, no worries. Relax. No worries at all. Oh my gosh. All right. I'm gonna assume everyone understood part B. But okay, part C. Yeah, don't make that same mistake again because we got the forces here of 110 newtons. So normal force from the floor, given that the magnitude of the normal force is Fn 110 newtons, right? Once again, we're gonna look at our normal force, and we don't have a component of the normal force pointing in the x direction, do we? We don't, right? So it's only in the y direction. So that would mean Fnx should be 0 newtons, and Fny, well, they already gave us 110 newtons. Wow, this is going to be very confusing for those who are going to be watching the recorded session because it's literally just going to be me laughing and you guys won't hear what went on. So good, cool, all right. For Fny, 110 newtons, since Fn is already pointing in the positive y direction, it's positive, right? So we just leave it as 110 newtons there. Sound good for part C? Cool. So then we have part D here, tension from the strap, given that the magnitude of the tension force is 20 newtons, and then that the angle theta here is 30 newtons. Or 30 newtons, 30 degrees. So we want to figure out Ftx and Fty, given that Ft is equal to 20 newtons. So this is 20 newtons. This is 30 degrees. This is Ftx, and that's Fty, right? So if we want to figure out Fty, this side right here, we're going to use a trigonometric function. Any idea which trigonometric function we would use for Fty? Would it be cosine for Fty? Sine, right? Because it's opposite over hypotenuse, right? So we want Fty over 20 newtons should give us sine over sine of 30 degrees, right? If it was cosine, cosine is adjacent over hypotenuse, right? So have to be careful with the whole trigonometric function thing there. But since we already kind of figured out how to do Ftx as well, Ftx is cosine, we'll just come down here and throw things in. So Ftx over 20 newtons should give us cosine of 30 degrees, and Fty over 20 newtons should give us sine of 30 degrees. And then we can just multiply things over here and here, right? 20 cosine 30, 20 sine 30, right? 20 sine 30. I do not have my calculator on me, unfortunately. But what is that? If I can remember my unit circle. I think that's cosine 30 is a half, right? Pretty sure. So that's 10 newtons, I think. Let me make sure here that I'm doing this correctly. Yeah, I think I have them mixed around. So yeah, because cosine would be your x coordinate and sine would be your y coordinate on a unit circle. Yeah, and that's, what is that? Y is 1/2, x is √3/2. I think. Yep. Mm-hmm. So this is 10 newtons, because sine of 30 would be 1/2. Cosine 30, that's √3/2, and so this should be like 17.3, I think. There. Yep. Went back to pre-calc and calc days in high school. So, believe that should be the answers for those two, 17.3 newtons and 10 newtons respectively for FTX and FTY. Sound good for everyone? Yeah, it looks like, okay, so FTX, yeah. I only got FTX 17.3 and FTY is 10. So if everyone's good for that part A, then part B here, it says using the components above, compute the x and y components of the net force, F net x and F net y, and then use those to determine AX and AY. So once again, this is just literally a repeat of what we kind of did, same principles for the last problem. So we have F net x, right? That's a compilation of all the forces in the x direction. So what are our forces acting in the x direction? Which forces are acting in the x direction here? Oh, I was just asking about, like, which forces were just in general, like not the answer, but I think that sounds about right. I'm not sure, but we'll check here in a sec. But yeah, just kind of repeat the question honestly. If we look at it in our x directions, we should have what forces for our F net x equation? Any suggestions, guys? There, awesome. FTX and FKX. FTX, and then we have FKX. So if you guys remember what I said earlier about the integrating the whole directions, right? Well, we have FTX, it's positive x, right? So we just keep that FTX, and we have FK, and we don't even really need to say FKX, right? Because we already know that the force of kinetic friction is only acting in the x direction, and so we don't really need to put the little x subscript there as well. So we can just say FK. So we can just erase, just erase the little x there and keep the k. But kinetic friction force is acting in the negative x direction, so we can go ahead and throw in a negative sign right there to integrate our direction within the equation itself. That's what I personally prefer to do. So we have FTX minus FK, and that's equal to MAX, right? And then we have F net Y is equal to what force is in the y direction? Fg, Fn, and Fty, right? Yeah, you can't forget about the y component of the tension. We have Fn and Fg, those are clear, right? But people always forget the components for any forces that are angled, right? So you have this angle for the tension force, you're going to have an Ftx and Fty. So we have to integrate Fty as well as part of the forces acting in the y direction. So we have, if we want to integrate our directions automatically, we have normal force in the positive x or positive y direction. So Fn is positive, Fg is negative, and Fty is positive as well. So we can say, okay, well, if we want to integrate the directions, Fn plus Fty minus Fg is equal to May, right? So, move this around here. We know that Fn is equal to 110 newtons, right? This is just a matter of plugging things in at this point. Fty, we said that was 10 newtons. And then Fg, we said that was what? 120 newtons, right? So this is where things get a little bit confusing now. They asked us for part A to put the direction, to put the sign, to put that negative in the Fg answer that we had, right? Now, if you make a mistake here and you just slide in negative 120 and plug it in, then you're going to get plus 120 at this point. Now, remember what I said about integrating your directions automatically. If you integrate your directions within the actual equation, all you have to do is put in the magnitudes. So if I have this negative sign here in front of Fg, I'm already indicating that it's in the negative y direction. So then all I have to do is just throw in the magnitude. So the magnitude of negative 120 newtons, right, or the absolute value of negative 120 would just be 120, right? That's if I choose to put this negative sign here from the begin with to integrate my direction. However, if you do it the way professors do it, if you feel that is easier for you, and you just say, I'm going to add up all the forces regardless of direction, Fn plus Fty plus Fg, right? If you add up Fg, then that's where you would have to plug in negative 120. So if this was plus Fg, you would see me saying, okay, 110 newtons plus 10 newtons plus negative 120 newtons. And then that would be minus 120 anyway, right? But I just prefer to have that negative sign from the begin with, so I can just say, I'm going to put in the magnitude right then and there. It just makes it easier for me. It's a lot easier to follow in my opinion, but I gave you guys both methods, so whichever one works best for you and whichever one you can easily follow, just stick with that. But I personally prefer integrating the direction automatically and just plugging in magnitudes of forces here. So, that being said, we have 110 newtons plus 10 newtons minus 120 newtons, right? Do the math real quick. This ends up being 0 newtons in the y direction, right? So, this is equal to May. What was the mass of the luggage here? They said it was 12 kilograms. So, obviously, you don't really have to continue, because if this is 0 newtons, then the acceleration due to the acceleration in the y direction would automatically be 0 then, right? If you just solve for this, Ay is 0, right? And it's kind of implicit too, because if there's no net force in the y direction, or for example, if there's no net force in the x direction, then automatically your acceleration is equal to 0, because F equals ma, right? If A is 0, then 0 times anything is 0, right? And so your acceleration has to be 0 if your net force is 0. And so that's kind of implicit. But at the same time, if you think about the nature of this problem, if the woman is literally just dragging this luggage across the floor, right? She's pulling it behind her. That luggage isn't levitating and it's not sinking to the floor, at least according to the details of the problem. So if you use your intuition, right, and you'll build this up as you go along and solve more problems, but if you have some kind of decent intuition with regards to these physics problems already, you can kind of assume that, okay, well, there's not going to be any net force in the y direction. No net force in the y direction, because this thing isn't moving upwards and it's not moving downwards. It's literally just being dragged across the x-axis or across the floor. Using your intuition is a bit of a risk at the beginning of physics. It gets a lot more developed as we go and practice more problems and get into more complex units. But yeah, I mean, it's something that you're gonna kind of develop naturally over time. But that's another way to kind of figure things out as well. Is like, okay, well, it's not levitating, it's not sinking to the floor, so there's probably not going to be a net force in the y direction, according to the details of the problem, because it just says that she's pulling her luggage, on the ref floor. So that's kind of a little bit of intuition that would help you confirm that your answer here is correct. So it's also kind of a sanity check as well. Because if you get like 2 meters per second squared as your answer, for whatever reason, you might have done some kind of calculation error, right? Let's say, for example, if you did plus 120 newtons on accident, right? And you get some kind of net force. Well, then I go back and I'm like, okay, well, what do the problems say? If I have a net force in the y direction, if I have net force in the y direction, does it make sense with the rest of the problem? Did the problem make any indication that this luggage is floating or it's sinking? Is it moving at all in the y direction? There's no indication of that in the problem anywhere. So that's how you would kind of use your intuition as well for physics when solving these problems, to kind of like realistically think about the situations and scenarios that you come across in these problems and be like, okay, well, this luggage isn't levitating, it's not sinking, so there's not going to be any net force in the y direction. So would it make sense for my answer to have, or my acceleration to be anything but zero? Kind of that, reasoning, essentially. So hopefully that kind of makes sense for AY. For AX, on the other hand, we're going to plug things in here as well. FTX was 17.3 newtons. FK, once again, they wanted us to indicate the direction here for FKX for negative 10 newtons, but I've already included the negative sign here when I'm writing my equation, so I just have to put the magnitude, right? So I just put 10 newtons. If this was F plus FK, right, then I would have to throw in that negative 10 newtons, right? So, because otherwise, like, it wouldn't make sense for these two to add up, 17.3 plus 10 newtons, because you can clearly see and even reason in real life that friction doesn't move in the same direction as your intended motion. It's always opposing your intended motion. So if I'm trying to move to the right, the friction is going to be moving against me to the left. So it has to make sense that your friction is opposite your intended motion. So if this FTX is for sure positive, right, then this FK, I have to subtract that from the FTX, right? So this has to be minus 10 newtons and can't be plus. Can't add them together. They have to oppose each other. So that's another way of reasoning and using your intuition to solve these problems. So this should be, as I believe Ellen stated earlier, this should be 7.3 newtons for your F net x, and this is equal to 12 kilograms times AX. And so if you divide those two, you should get your AX there. I think that's 7.3 divided by 12, right? That should get you somewhere around 0.61 meters per second squared. And once again, your answer here is positive for acceleration. Kind of makes sense, right? Because if there's a net force that's positive, it's a positive 7.3 newtons. So my net force is to the positive x direction. It's moving to the right. So if I'm moving to the right, it would make sense that my acceleration would be positive in that case. Because my net force is positive, my acceleration should be in the same direction, or should have the same sign as my F net. Any questions at all about problem 2? Any questions at all? Nope. Okay. Alrighty. So, problem 3 now. Final problem here. I'm hoping, I don't know if we're going to get done early, but we'll try. Once again, this is really just a repeat. Two people are moving a box across the floor, as shown in the figure below. First ties a rope to the box and pulls with a force F pull with a magnitude of 65 newtons at an angle of 37 degrees from the negative x-axis. And then the second pushes with a force magnitude 82 newtons at an angle of 23 degrees from the negative x-axis. The mass of the box is 25 kilograms. And there's no friction between the block and the floor, right? So no friction. So we're not going to have any kinetic friction here at all, right? And we know that it's kinetic friction because it's a box sliding. It's an object sliding against a surface, right? So, yeah, we don't have any kinetic friction there. We have our mass. And now for part A, we want to draw a free body diagram including all of these forces. So, we already have our F pull and F push forces. Those are indicated already, right? What other forces are acting on the box? So we have, let me draw F pull here. F pull would be 37 degrees from the negative x-axis. So if we take the negative x-axis, raise it up like that, we should get 37 degrees. And then we have, this is F pull, right? And we also have F push, right? Because you imagine this thing pushing down like that. And that's what? 23 degrees from the negative x-axis. 23 degrees from the negative x-axis. Oh, you can't see my writing? Okay, let me stop sharing and re-share here. Okay, is that better? This is F push. It is better. Okay, so yeah, F pull, F push, and then someone said gravity. Yep, absolutely right. We have gravity, right? FG. And we have, what else? So yeah, Ellen said normal. Okay, cool. Normal. And that's it, right? Because we don't have any kinetic friction. So normal force as well. Now we got to indicate the superscripts, which for future reference, you probably won't have to do a lot of superscripts in the future unless they specifically indicate that you do. Yeah, it's kind of a hassle. So I would literally just write the subscripts from now on unless they specifically indicate that they require superscripts. It's just a lot quicker. But for normal force, right, it's that similar kind of deal with the luggage, right? It's the floor acting on the box. The gravity is acting, or the earth is acting on the box, right? Because the force of gravity is due to the earth, gravitational force. The push, well, that's just a push, right? So we can just say that like maybe person on box. Let me move that over. Person on box, right? For example. And then we can say pull, also person on box. But yeah. Now here's the key. It says make sure the lengths of the vectors represent each force are qualitatively correct. So you got to make sure the length of your normal force, the length of your gravity, and all that makes sense with the values that you're going to end up calculating. I mean, really, it kind of comes down to the calculations that you do later on. Here we know for sure now that we've kind of drawn things out correctly. We've drawn them out correctly. We might not be sure about the lengths of the values here for the vectors, but through our calculations, we're going to figure out those values. And then if need be, we can go ahead and adjust our lengths of our vectors. So for example, if we figure out later on that normal force is actually smaller than the force of gravity, right? Then we might draw this a little bit. We can erase and draw it a little bit smaller, for example, right? So I would make sure that you at least have your directions and everything correct. And then, oh, you guys' screen is frozen again. Okay, 1 second. Hopefully you can see it now again. But yeah, basically I would just make sure that your drawing is correct in terms of like making sure the directions and all that makes sense. But then, if need be, you can adjust your drawing, make some erase marks, fix the lengths and all that based on your calculations. At least that's how I did things back in the day. So I would just go ahead and draw it the best I could, draw the lengths as best I could proportionally. And then I would go back and adjust if I needed to based on the calculations that I got. But yeah. But I would say try your best to get it right the first time, because your calculations could very well be wrong. And then you go back and you could mess up the drawing too. So you might lose points both ways. But like I said, just try as best as you can to get the lengths proportional. Right? But yeah. So I'd say like, yeah, this is pretty good. Okay. So we can figure out now for part B. It says determine the x and y components of the forces by the two people, F pull and F push. So there's F pull X, right? F pull Y, F push X, F push Y, right? And naturally, since we have angles and we have magnitudes for these two vectors, we can kind of figure things out with trigonometry, right? So F pull X, this right here is F pull X, right? And this is F pull Y. So F pull X, how can we figure that out? Cosine or sine? Cosine, right? So F pull X over, what was the magnitude again? Let's see here. 65 newtons, right? So F pull X over 65 newtons, that's adjacent over hypotenuse, is equal to cosine, and that was 37 degrees, right? So naturally, the other one will be sine, right? F pull Y over 65 newtons, that's opposite over hypotenuse. That's equal to sine 37. For F push X and F push Y, X is going to be what? Cosine or sine for F push X? For F push X here would be sine. This is F push X. Yeah, cosine, right? Because it's adjacent over hypotenuse. And that's adjacent to the angle, or next to the angle, basically. So F push X over, that was 82 newtons, I believe, is equal to cosine 23 degrees. I'm going to check that. 82 newtons and 23 degrees, yeah. And we have F push Y over 82 newtons, and that's equal to sine 23 degrees, right? Because F push Y would be opposite over hypotenuse to the angle, right? And that's of sine 23. So we just multiply things over, basically, and calculate things out. So 65 cosine 37, what did you guys get for that? Any takers? 65 times cosine 37. $51.9, there we go. However, 51.9 newtons, and that's negative 51.9 newtons, right? Because when we're doing our trigonometric functions, they're only going to give us magnitudes. Now, you have to look at f pull x now. F pull x is directed to the negative x direction, so then you have to add your additional negative sign there to indicate your direction. So this has to be negative 51.9 newtons, right? Because it's pointing in the negative x direction. How about f pull y? 65 times sine 37. What did you guys get for that? 39.1. There we go. 39.1 newtons for f pull y, right? So this is in the positive y direction, so makes sense, right? We don't see any negatives there. How about f push x? Let me push things down here. So that's 82 times cosine 23, and that's 75.5, but once again, you got to make the distinction. You got to check again. F push x is this way, right? So it should be what? Negative 75.5, right? Excellent. And then F push y, we have 82 newtons times sine 23. What do you guys get for that? (32), and it also has to be negative 32 newtons, right? Because F push y is also pointing in the negative y direction. Have to make sure that you're checking your no worries. You just have to make sure that you're checking your final answer and make sure that it kind of matches up with the directions you've drawn. And once again, that's kind of like your sanity check too, right? Because if you don't have this drawn correctly, at least in terms of the directions and stuff, you're going to get these wrong because these are only going to give you magnitudes. So you have to put in the negatives or keep them positive based on what you've drawn up here. So yeah, that's part B. Any questions about part B at all? Let's see here. Nope. Okay. All right. So part C here, right? It says use Newton's second law in the y direction to determine the magnitude of the normal force exerted on the box by the floor. Magnitude and direction of the normal force, all right, exerted on the box by the floor. So we need to figure out Fn. You need to figure that out, right? And it says Newton's second law, right? So it would indicate that we need to set up a F net equation, right? So in this case, it's in the y direction, so this is F net y, right? And we want to figure out normal force. So we're only concerned with the forces acting in the y direction at this point. So what are those forces that are acting in the y direction? All of the forces, right? All of the forces have a y component. Fn, Fg, F pull y, and F push y, right? So we have Fn positive, right? We have F pull y, right? And then we have minus Fg and minus F push y, right? Once again, I'm integrating those negative signs automatically into the equation, so I can just plug in my magnitudes as opposed to trying to go ahead and plug in the directions and stuff. So if I just put in the negative signs here, I can just plug in the magnitudes of everything and be okay at the end. Because in the end, I want to figure out the magnitude, right? So with Fn, figure that out, right? And actually, there's a second component to this, and that's, well, F net y is equal to MAy, right? But we already said that this box is moving across the floor. So what does that indicate about the F net y if it's just moving across the floor? Awesome, right? It's 0. F net y is 0. Because it's moving across the floor, it's not levitating, it's not sinking to the floor, so we can automatically kind of assume that F net y here is going to be 0, right? Because because the problem says that the box is moving across the floor, therefore 0 net force in the y direction, right? Obviously, if it's moving across the floor, there is a net force in the x direction, though. But we're not concerned with that just quite yet. So we have Fn, F pull y, we already figured that out. That was 39.1 newtons, minus Fg. We know that the box is 25 kilograms, so we can figure that out. Fg is equal to mg. That's 25 kilograms. And since I'm going to be plugging in the magnitude, I don't have to put in negative 10 meters per second squared. I can just put in 10 meters per second squared. That's going to give me 250 newtons, and that's my magnitude. Because like I said, when I integrate the sign into the equation, I'm just plugging in the magnitude. So I just plug in a positive 250 newtons. And the negative sign there is going to take care of the direction. Otherwise, if this was plus Fg, then I would have to put in that negative 10 meters per second squared, and therefore I'd have to put in plus negative 250 newtons. And then F push y, figured that out as well. This was the negative 32 newtons. Once again, this integrates direction here for that answer because they wanted us to find the directions, right? They wanted us to indicate the directions here for part B because they didn't ask for magnitude. If they didn't ask for magnitude, be sure that it's always asking for direction. So you have to indicate the signs in your final answers. But since, like I said, I'm integrating the direction here within the equation itself, I just have to put in the magnitude. So I just put in the absolute value of that answer, which is 32 newtons. Because otherwise I'll get, if I do negative 32 newtons, it's going to add them up together, and that's not right. So I just want when I integrate those signs into the equation, I put in magnitudes for everything. So there's minus 32 newtons. And then if I do some algebra right, I should be able to figure out what my Fn should be. Right? And I believe this should be around 242.9 newtons. And this is, they want us to indicate the direction, I think, right? Or did they? Yeah, no, they just said use newtons like along the y direction to determine the magnitude. Yeah. So you can just say 242.9 newtons, and that's the end of it, right? If they were to ask you, okay, well, what's the direction? If they asked the magnitude and direction, you would say 242.9 newtons in the positive y direction, or upwards, for example, 242.9 newtons upwards. But yeah, makes sense for part C? Cool. Alrighty. Part D now. Determine the magnitude and direction of the acceleration of the box. So, if we're trying to figure out the acceleration of the box, well, we know that the box was moving across the floor. So, if we want to figure out acceleration, we're going to use a F net equation, but this time is going to be F net x. Right? F net x. Why? Because obviously, if we're moving across the floor, that's in the horizontal direction, it's in the x direction, right? So we're going to set up an F net x equation, right? And then if I think about it, if I'm pushing here and I'm pulling this way, right? Both my F pull x and my F push x are in which direction? Negative x, right? Yeah. So then how would we write the equations integrating F pull x and F push x? How do we kind of write equations similar to this one? How do we set it up? Yep, excellent. Negative push x minus F pull x. Alternatively, like I said, you can say F push x plus F pull x. So you just add up all the forces, but then that would mean you would have to put in any of the signs. But if you do it this way, where you indicate the direction from the begin with, you can just plug in magnitudes like I said. So F push X and F pull X. These are the values that we're going to use. Like I said, we've already integrated the directions in the equation, so we're just going to take the absolute value, right, to figure out the magnitude. So we don't want to put negative 51.9 newtons. What is this? F pull X. So we want to put in minus 51.9 newtons like that, because we don't want to do minus negative 51.9 newtons. We just want to put in the magnitude, 51.9 newtons. And then F push X, this was 75.5 newtons. We're just going to put in the magnitude. That's negative 75.5 newtons. Because otherwise, if we put in the negative 75.5 newtons, it would be like saying negative 75.5 newtons, and that would be positive overall. And that's not the case. We want to make sure that everything is making sense, because if we indicate the direction in the equation, we're just putting in the magnitudes, just the magnitudes. The negative signs are taking care of themselves. If we want to do F push X plus F pull X, if we want to add things up like this, right, then you'd have to put in, okay, negative 75.5 newtons minus, or essentially plus negative 51.9 newtons. It ends up being the exact same math, right? It ends up being the exact same math. It's just that I feel that it's much easier if you integrate all the directions first and then just plug in the magnitudes of everything. Because otherwise some people might get confused and, I guess mess up their signs and whatnot. But anyway, for F net X then, we know that this is equal to max, and our mass was 25 kilograms, and we need to figure out the acceleration in the x direction. And then this is equal to negative 127.4 newtons, I believe. Right? And then, yeah, you just go ahead and solve for your AX. Let me know what you guys got. Negative 5.1 meters per second squared. Now, here's where it gets a little trippy sometimes. You know for sure that your answer is right here, right? But they want you to figure out the magnitude, right? So, this negative sign, you just have to take the absolute value of it. So you can literally just put up two bars like this and just say, okay, this is at 5.1 meters per second squared, and say that this is, because obviously they want you to indicate the direction, so you'll say negative x direction, or west, for example, or left, right? Now, like I said, if you were to do F push X plus F pull X, right, if you were to put in negative 51.9 newtons minus 75.5, right, if you do that as well, you'll still end up with that negative 5.1 at the end, and you have to take the absolute value of it. The other way, if you wanted to directly get the 5.1 positive, right, is if you were to just throw in a negative sign here. And that negative sign comes from your intuition as well, right? Because if the box is moving left, right, there's a net force left. So that net force has to be negative. Well, the mass is positive, so the only way we're going to get a negative sign is if we throw in a negative sign for our acceleration. So if you have 25 kilograms times negative AX is equal to this negative 127.4, right? Then if we solve things, we're going to get that positive 5.1. Really doesn't matter, just as long as everything is kind of consistent to a certain extent and you're matching what they need from you, right? Because, I mean, what matters is this part right here. For this part, we threw in max. We didn't throw in a negative sign, right? That meant that we ended up with a negative answer at the end. If you ended up with a negative answer, right, that's fine. If they're asking for magnitude, just simply take the absolute value at the end and you're good to go. You're adjusted. So a lot of this force stuff is a matter of adjusting yourself to the conditions and the requirements asked of you in the problem. So with regards to, for example, the free body diagram, right, we figured out gravity, that was 250 newtons, right? We figured out Fn, so that was 242.9 newtons. So if 250 plus, or compared to 249, right, what 249 or yeah, 242. So that means we kind of have to go back a little bit and maybe adjust this to where it's just a tiny bit smaller than Fg, for example, right? Just to make things proportional. And then F pull Y and F push Y, right? You might draw your vectors then for F pull generally, or kind of adjust them in a way that your forces here kind of make sense. I wouldn't dwell too much over it, just as long as it like visually looks okay and it kind of makes sense, you're good. That's not something that they'll like destroy you over. What's most important is that you kind of have everything figured out in terms of the directions. But if it's something like really obvious, right? If it's something way obvious, like if this net force was like 50 newtons or 100 newtons theoretically, right? Then that's a big difference, and so we would have to for sure draw gravity bigger than the normal force. But yeah, that's kind of your sanity check. That's how all these, like your free body diagram, it's kind of like your cause and effect, and so are the problems as well, because what you get here for your calculations, you can check that they make sense with the free body diagram if you have that drawn correctly. At the same time, once you get your calculations like these, you can use those to correct your free body diagram in case you were kind of iffy about it from the begin with. All right? So that's how these free body diagrams and the problems are kind of codependent on one another to make sure that you have everything right. But that's the gist, really, of the whole force unit. We're going to get a lot more in depth with different forces throughout the semester. There's going to be a lot of cool things that we do. But yeah, that sounds, I don't know if you're interested in physics, if that sounds cool to you, sure. I'm not necessarily interested in physics per se. I just, I'm gonna be honest, like I struggled with it. And so it's just for me, it's more kind of like an achievement, I guess, or an accomplishment, because I struggled massively in high school with physics. And I tried really hard to do well in college. So you don't necessarily have to be interested in physics. It's one of those subjects that I feel like you can kind of directly apply in daily life, essentially. Or at least once you kind of understand the concepts, it kind of, things kind of make sense if you try to think about things in a physics sense. So in the next couple of weeks, we'll get into things like torque, for example. And so you might think about torque when like you're opening a door or something like that, right? If you're opening a door, adjusting where you push the door will adjust how easy or hard it is to open it, for example. So if you're pushing at the hinge, it's not going to open really well, as opposed to if you're pushing kind of towards the doorknob, right? Anyway, that's just kind of the gist of this stuff. Things are pretty interesting, I guess. They kind of relate to some real life scenarios and stuff. So hopefully everything kind of made sense and my explanations made sense. But okay, someone wanted to go back to 3A. There. If you want to take a screenshot or something or write things down real quick. Yep, and then 3D. This was 5.1 meters per second squared. That's the magnitude. And then in the negative x direction. But yeah. Any other questions at all? Yep, no problem. Have a good night, guys. I mean, if you guys are ready to head out, that's all fine with me. Alrighty. No problem. I will go ahead and end the recording as well.